Welcome to this lecture on ring theory. Today, we are going to explore the definition and examples of rings. We will start by thinking about basic arithmetic, something you have known since childhood, and see how mathematicians have generalized these rules to create a universal framework for algebra. By the end of this video, you will understand exactly what a ring is and how to prove a set forms one. Before we look at the formal math, let us understand why we need this concept. You know exactly how to add and multiply standard numbers. But what if we could add and multiply other strange things like hours on a clock face, grids of numbers called matrices, or abstract algebraic polynomials? A ring is simply a mathematical playground where we are allowed to do exactly two things: add and multiply. Think of it like a video game that gives you exactly two buttons to press. To make sure the game does not break, these buttons must follow a strict set of predictable rules. Now that we understand the goal, let us look at the exact mathematical rules that make a ring. For a set to be a ring, it must pass three major tests. First, under addition, the set must form an abelian group. This means you can add items in any order, there is a zero element, and every item has an opposite that cancels it out. Second, under multiplication, the set must be associative, meaning the grouping of elements does not matter. Finally, the two operations must connect to each other through the distributive property. Let us look at the specific formulas for these rules. This brings us to our first critical rule, called closure under addition. Conceptually, this means our mathematical universe is a sealed box. If you take any two elements from our set and add them together, the result must also be inside the same set. You cannot add two things and get an answer that belongs outside. In this formula, A and B represent any two elements we pick, and capital R represents our ring. If this rule holds, it guarantees that our addition operation is safe, predictable, and completely self-contained. If the result escapes the set, the ring is broken. Moving on to the next requirement, we have the rule for the additive inverse. This rule ensures that every element has a negative counterpart. For every item you pick, there must be another specific item in the set that cancels it out perfectly. In our formula, A is the element we choose, negative A is its inverse, and 0 is the additive identity. When you add an element and its inverse together, they must bring you exactly back to the 0 element. This is a crucial property because it is what allows us to perform subtraction within the ring. Finally, we have the distributive laws, which act as the bridge connecting addition and multiplication. Without this, the two operations would have nothing to do with each other. This specific formula shows left distribution. It means if you multiply an element A from the left side against a sum of B and C in parentheses, the multiplication spreads out. The outside element multiplies against each part of the inside sum individually. This is exactly how you expand brackets in basic high school algebra. If a set passes all these formula checks, it officially becomes a ring. Before we move on, let us see this with a concrete example. We will test the most familiar mathematical system in the world, the set of all integers. This includes all positive whole numbers, negative whole numbers, and 0. We want to verify if this set forms a valid ring using standard addition and multiplication. Let us verify the additive inverse rule using a specific integer. If we pick the number 5, we know that negative 5 also exists in our set of integers. When we add them together, they perfectly cancel out to give 0, which is our additive identity. Continuing with our integer example, we must now check the distributive property. We will evaluate the left side of the rule using the numbers 2, 3, and 4. We first add 3 and 4 inside the parenthesis. This gives us a sum of 7. Then we multiply that sum by the outside number, which is 2. 2 times 7 gives us a final result of 14. This gives us a clear target to match when we test the other side of the rule in the next step. Now we evaluate the right side of the distributive rule to see if it matches our target of 14. We multiply 2 by 3 to get 6, and we multiply 2 by 4 to get 8. Adding 6 and 8 together also gives us 14. Since both sides match perfectly, the distributive law holds true. Because all the other rules of addition and multiplication also hold naturally for whole numbers, we can confidently conclude that the set of integers is a perfect example of a ring. Physically, this means standard arithmetic is perfectly stable. Now that we have seen a standard example, let us look at a system that is a bit more unusual, called modular arithmetic. Imagine a clock that only has 4 numbers on its face: 0, 1, 2, and 3. In this system, whenever we count past 3, we wrap back around to 0. We want to see if this small, restricted set can form a valid ring. First, we perform standard addition with 2 numbers from our set. 2 plus 3 gives us 5. However, 5 is not in our allowed set of numbers. To fix this, we must apply our wrapping rule to bring the number back into the allowed universe. We divide 5 by 4, which goes in one time with a remainder of 1. In modular arithmetic, we only care about this remainder. So in this specific ring, 2 plus 3 actually equals 1. This proves that the set is closed under addition because the answer wrapped back into our allowed set. Now let us test multiplication. If we multiply 2 by 2, the standard arithmetic answer is 4, which is again outside our set. We must apply the exact same wrapping rule to find the true answer for our multiplication. Dividing 4 by 4 leaves a remainder of exactly 0. Therefore, in this ring, 2 times 2 equals 0. Even though this looks very strange compared to normal math, it perfectly follows all the strict rules of a ring. The operations are closed, associative, and distributive. This proves that rings do not need infinite numbers to exist. Even a tiny looping set of 4 numbers can be a fully functional ring. Let us visualize what we just proved with our examples. This diagram summarizes the most fundamental requirement of a ring, which is closure. Look at the large outer circle representing the ring R. Inside, we have elements A and B. Notice the arrows pointing from these elements into the addition and multiplication machines? The most important part of this diagram is where the output arrows go. They point directly back inside the large circle to A plus B and A times B. The system is completely self-contained, separating a true mathematical ring from a broken collection of numbers. You might wonder why mathematicians spent so much time inventing these abstract rules. The reason is that rings are the hidden engine behind much of modern technology and advanced science. For example, the secure encryption that protects your bank passwords and private messages relies entirely on rings of modular arithmetic, exactly like the clock math we just explored. In computer science, error-correcting codes use polynomial rings to fix corrupted data when streaming videos or sending pictures from space probes. It is a universal toolkit for problem solving across different universes of numbers. To summarize our lecture, a ring is simply a mathematical set equipped with 2 well-behaved operations, addition and multiplication. We learned that addition must act like a standard group with a 0 element, and multiplication must be associative. Most importantly, these 2 operations must link together smoothly via the distributive property. Whether you are dealing with whole numbers, matrices, or looping clock numbers, if these specific rules are met, you have successfully built a ring. You have now mastered the foundational definition of ring theory.